Okay, we're gonna now talk about some examples of random variables and their probability mass functions, how they get calculated. So let's start with, we're gonna do this for, we're gonna do several examples here. Many of these should be familiar, and we'll see how they sync up with the definition that we're how they sync up with the definition that we've been talking about. So let's start with dice. In this case, we're going to let u be a function well, we consider the omega to be the outcomes of the roll of a die, six-sided die. And we're going to define u to be function from 1 to 6. Remember how we define square bracket 6? That's just the first 6 positive integers. And the way we define this is we're going to record number of dots on showing on top of the dot. Okay. Then in this case, the mass function for u is 1/6 for each possible value of u. And we say that u is uniformly distributed on the set 6. So important to note that there is a difference between the values that the random variable takes, 1 up through 6, and the outcomes of the dot. Even though in principle that's kind of the way we naturally refer to them. Okay. Okay. Let's consider now the case of 2 six-sided dice. So with 2 six-sided dice, we're going to let t be a random variable. Recording the sum of the values on 2 fair six-sided dice. What do we mean by fair? Fair means uniform on all of its outcomes on the outcomes 1 up through 6. Okay, so we've already calculated this a number of times. We calculated this in our Craps analysis. And so remember, in our Craps analysis, we calculated I'm not going to write it all out, but we calculated that the probability of a 2 is 1/36, 3 is 2/36, 4 5, and so on. And all the way back down to 1/36. So if we actually were to draw a picture of what this looks like, well, first we can write this as a function, P sub t of t can be expressed as 6 minus the absolute value of 7 minus t quantity divided by 36. This is for all values of t from 2 up to 12. So you should verify that this is accurate. Verify that if we plug in, for example, the value 4 here, just to do a little quick example, the value of 4 would be 6 minus absolute value 7 minus 4 over 36. This is 6 minus 3 over 36 is 3 over 36, which is exactly what we calculated. So this is a general formula that allows us to express this probability table in one simple closed form. And this is called the triangular distribution. From 2 to 12. Now, why do we call it that? Is if we were to plot the probability mass function, so let's let P sub t of t be this on this side. And then we have 1, 2, 3, 4, 5, 6 here. And then here we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, if we plot the masses as kind of vertical rods, so there's a mass concentrated at each of these, and the height is the corresponding mass. So these would be the masses. And what we easily see visually in doing this is that the distribution looks like a triangle. Starting at its low point on the left-hand side at 2, going up to its peak at 7, and then coming back down to 12. This is a plot of the probability mass function. Okay, let's consider another case, one we're familiar with coin tossing. And what we're going to think about doing is we're tossing a coin n times, little n times. So let's let capital N be the number of heads that occur in lowercase n tosses of a p coin. So we're counting, n is the random variable. I should say, in all of these cases, the way that we write random variables is, generally speaking, there's no requirement, but we generally are going to use capital letters X, Y, Z, W, T, U. Could be really anything we want, but it's the convention to use capital letters. So here we're using capital letter N. to count the number of heads that occur in little n toss of a p coin. Let's let little n be bigger than or equal to 1. And what is the answer to this? Well, the probability that there are exactly k heads tossed. So this is the mass function. Remember how we calculated that before, is that there are little n possible spots for heads to occur. But when we fix k, only little k can occur there. So if we define the heads as appearing, let's say, in these positions, how many different orientations among the n slots are there to put k heads? There are n choose k. Each one has probability p, and they're all independent. So they multiply together, p to the power k, and then each of the rest, the n minus k remaining, are all going to have to be tails. They all have probability 1, independent probability 1 minus p. So what we're left with is this expression. And this is a well-known distribution and has the binomial distribution. With little n trials. And success probability p. So and then to write this in shorthand, we often would write n is distributed as binomial np. So what's important to understand here is that this definition of a success, it doesn't necessarily have to be in real life anything that we would think of as a success or failure. The point is that the idea of success is tied to the number of whatever, number of heads. So if we wanted to count the number of tails, then that would be tails would be considered a success. So the binomial distribution is how we count some specific, how many times a particular outcome occurs in some collection of trials. And the thing that we're counting, the probability of the thing that we're counting, of the outcome that we're counting, is what's called a success in this terminology. All right. Here's another one. Let's let W be the number of tosses required to produce the first head. So we're tossing a P coin. And what we're going to do is we're going to actually toss it until the first head appears. So what is actually the sample space here? The sample space are sequences that essentially look like this. T up to head, where this can be anything k times k, anything from 0 up to potentially infinite. So we're going to toss a coin until the first head appears, and we're going to count how many tosses that requires. So in this case, for example, if we had t, 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 and then a head, then the value of this random variable is 4. Okay. So then in general, how does this work? In general, for any given W, let's write it as, say, K. For any given K, what happens is we have K minus 1 tails, each independent and having probability 1 minus P. So there's K minus 1 of them. 1 minus P of the K minus 1 power times the probability that the next one is a success. In this case, we say that W has the geometric distribution with a success probability. P. And again, success here has to do with we're the terminology is that we assume that we call it a success if once we stop. So the criteria for us to stop is called a success. Shorthand, we would write W is distributed GOP. Notice here that the range of W in this example is the set of non-negative integers. Set of positive integers, I should say, which is a countable set. So it's actually an infinite set, but it's countable. One final observation, which I should have probably said earlier. So let me actually move this down. Is that if we look at the binomial distribution, we were imagining that we toss a coin some fixed number of times, little n. If we only toss the coin once, so a single binomial trial. So if we take n to be 1, in this case, we have a random variable x with number of trials 1 and success probability p. This is called a Bernoulli trial or a Bernoulli random variable. It's called a Bernoulli random variable with parameter p. We write that as x Bern p. It could also be written as binomial 1p. And the probability mass function is, in this case, p if x equals 1, 1 minus p if x equals 0, and otherwise has 0 mass. So it's just a random variable that takes the values 0 and 1. And another way to write this, though, would be formulaically p to the power x, 1 minus p to the power 1 minus x, if x is 0 or 1, and 0 otherwise. Okay, so those are some examples of random variables. These are all cases that we've more or less seen before. We haven't talked about the geometric distribution just yet. We've seen the binomial distribution, we've seen the triangular distribution, we've seen the uniform distribution on a finite set. This is the random variable version, so we're regarding the outcomes here as a function of, the output is a function of the outcome of the experiment. Okay. And now next time, what we're going to talk about, so a lot of how we build more complex probability models out of simpler ones is that we take a simple one and we attach additional assumptions to it. One of the things we did, that's exactly what we did in the case of the Bernoulli or the binomial case, where we have a Bernoulli trial. A single toss of a coin is pretty easy to model and to understand. It's just either a 0 or 1 with probability p, or 1 minus p respectively. But if we string together some independent tosses of that coin, we can get a binomial random variable by adding up the results of n independent tosses. We're going to formally define what it means to have independent random variables, and we're also going to talk about the concept of a distribution function, which is another way to represent a distribution beyond the probability mass function that we talked about so far. So we'll do that next time.